Good guys. In the following set of videos, we'll be taking a look at the various applications of first order differential equations. And for this first order differential equation series, I'm going to be looking at 4 case studies or 4 applications. And the first application we are going to be taking a look at is in the areas of electric circuits or electrical circuits. Then we're also going to be taking a look at its use in heat conduction. And third one we're going to be looking at is in chemical action. And the last one is in vertical motion. So, and for each of these applications, we are going to be taking a look at some questions under them. So let's kick it off with electrical circuits. So for its application in electric circuits, let's take a look at this question. So we're required to solve the equation L di dt plus Ri to be equal to E naught sine omega t. Where L, R, and E naught are constants. And we're also asked to discuss the case when T increases indefinitely. Now let's take a look at the solution. To start with, let's divide through by L. On doing that, we now have the I dt plus R over Li is equal to E naught over L sine omega t. Now this looks very familiar as it takes the form of linear differential equation of the first order. Remember that the general form of linear differential equation is y dx plus py is equal to q, where p and q are functions in x. So to solve this differential equation, we are going to be using the same method as that we've discussed when we are solving first order linear differential equations. So the first thing is to get our integrating factor. Our integrating factor will be equal to e raised to the power of the integral of r over L with respect to t. So this gives us e raised to the power of r over L t. So we've obtained our integrating factor that way. And recall that the solution will be our integrating factor multiplied by the dependent variable, which is I in this case, will be equal to the integral of the integrating factor e raised to power r over L multiplied by t multiplied by E naught sine omega t divided by L with respect to t plus an arbitrary constant. Now let's simplify this. We have I e raised to power r over Lt will be equal to E naught divided by L integral of e raised to power r over L multiplied by t sine omega t dt plus a constant. Let's just consider the integral of e raised to power r over Lt sine omega t with respect to t. So we can solve this using integration by parts. So now let's let u be equal to e raised to power Rt over L and the v be equal to sine omega t dt. So we now have that du will be equal to r over L e raised to power Rt over L and v on integrating both sides will be equal to minus cos omega t divided by omega So now recall that from integration by parts, integral of u dv is equal to uv minus the integral of v du. So substituting these values, we now have the integral of e raised to power r over L t sine omega t dt to be equal to uv, which is e raised to power r over Lt multiplied by minus cos omega t divided by omega minus the integral of v du, that's minus cos omega t divided by omega multiplied by r over L e raised to power Rt all over L with respect to t. So we now have the integral to be equal to minus e raised to power r over Lt cos omega t plus r all over L omega cos omega t multiplied by e raised to power Rt all over L with respect to t. Or you can write it as e raised to power Rt over L multiplied by cos omega t. So we still have to simplify this particular integral here. So similarly, using integration by parts, we have that the integral of cos omega t multiplied by e raised to power Rt over L with respect to t be equal to e raised to power r over L multiplied by t divided by omega sine omega t minus r all over L omega integral of sine omega t e raised to power RT over L dt. So since we have this, you can confirm this. We can now substitute it into the original integral. Let's call that equation asterisk. So I'm going to write that on the next page. So now we have that the integral of e raised to power RT over L sine omega t with respect to t is equal to minus e raised to power RT over L divided by omega cos omega t plus R divided by L omega integral of e raised to power RT over L cos omega t with respect to t. And we also know that the integral of e raised to power RT over L cos omega t with respect to t is equal to e raised to the power of RT over L divided by omega sine omega t minus R divided by L omega integral of e raised to power RT over L sine omega t dt. So we can now substitute equation 1 into equation asterisk. On doing that, we have the integral of e raised to power RT over L sine omega t dt is equal to minus e raised to power RT all over L divided by omega cos omega t plus R over L multiplied by everything in equation 1, which is now e raised to the power of RT all over L divided by omega sine omega t minus R divided by L omega integral of e raised to power RT all over L sine omega t dt. So you can then simplify this to become minus e raised to power RT divided by L cos omega t divided by omega plus R divided by LW or L omega. Sorry, this R divided by L omega here. So R divided by L omega squared e raised to the power of RT over L sine omega t, then minus R squared divided by L squared omega squared integral of e raised to the power of RT over L sine omega t dt. So this is same thing as e raised to power the integral of e raised to power RT over L sine omega t dt. So we can see that this and this are common, so we can collect like terms. So on collecting like terms, we have that 1 plus R squared divided by L squared omega squared multiplied by the integral of e raised to the power of RT divided by L sine omega t is equal to e raised to the power of RT over L divided by omega, right, there's a minus sign here, cos omega t plus R divided by L omega squared e raised to power RT divided by L sine omega t. We can then factorize e raised to power RT over L out in the right hand side. So we have 1 plus R squared divided by L squared omega squared multiplied by integral of e raised to power of RT over L sine omega t dt. Same thing here will be equal to e raised to the power of RT over L multiplied by R sine omega t minus L omega cos omega t divided by L omega squared. So we now have the integral of e raised to power RT over L sine omega t dt to be equal to e raised to the power of RT over L multiplied by R sine omega t minus L omega cos omega t divided by L omega squared multiplied by L squared omega squared divided by R squared plus L squared omega squared. Now this came from dividing both sides by 1 plus R squared over L squared omega squared, which is 1 divided by, on simplifying that, we have L squared omega squared into bracket, the numerator now becomes L squared omega squared plus R squared. So when you do this, you're going to be having L squared omega squared divided by R squared plus L squared omega squared. So we now have that the integral of e raised to power RT over L sine omega t dt will be equal to e raised to the power of RT over L multiplied by L into bracket R sine omega t minus L omega cos omega t. So this divided by R squared plus L squared omega squared. Now if we go back to the original solution, we have that I e raised to power RT over L is equal to E naught divided by L multiplied by this integral we just obtained plus a constant C. It's good to know here that C is a constant because in electric circuits, C can also represent capacitance. So I think we might want to change that to D instead. So let's use small letter d as a constant to avoid any form of confusion. So now we are going to bring this back. So now we can recall that I e raised to power RT over L is equal to E naught divided by L multiplied by the integral of e raised to power RT over L sine omega t dt plus the constant d. So to simplify this, we can substitute e raised to power the integral of e raised to power r over RT over L sin omega t with respect to t in this. So you have I e raised to power RT divided by L to be equal to E naught divided by L multiplied by L e raised to power RT divided by L multiplied by R sine omega t minus L omega cos omega t divided by R squared plus L squared omega squared plus D, which is a constant. So we can simplify this to give I e raised to the power of RT over L is equal to E naught e raised to the power of RT over L multiplied by R sine omega t minus L omega cos omega t divided by R squared plus L squared omega squared. Then plus D. Can now divide through by e raised to power RT over L, and we have I to be equal to E naught to bracket R sine omega t minus L omega cos omega t divided by R squared plus L squared omega squared plus D e raised to the power of minus RT over L. And this is going to give us the solution to the electrical circuit problem. So we're also asked to examine the case where t goes to infinity. So if t goes to infinity, we know that e raised to the power of minus RT over L is going to tend towards 0. So therefore, our I now becomes E naught to bracket R sine omega t minus L omega cos omega t divided by R squared plus L squared omega squared. And this is our result. Thank you very much for watching this video. I hope you guys enjoyed it.